Okay, good morning. So today we will continue the previous lecture of 741 IC. So in last lecture, we have seen the complete schematic of 741 IC. So in this structure, total 23 transistors are there, one capacitor and few resistors are there. So all the bias circuitry is shown within red color, while the input stage is shown in dark blue color, and gain stage, which consists of transistor Q16 and 17, this is in blue color, while the output stage comprising transistor Q14 and Q20, class AB output stage is made up of by transistor Q14 and Q20, and this is the transistor Q22, 24, 21, 25. This is for short circuit protection. So in last class we have discussed all these topics in detail. So now we will perform the DC analysis and then we will see the AC analysis. So in today's lecture we will perform the DC analysis. So what is the purpose of DC analysis? So we have to find collector current of various transistors. Once we will find the collector current of various transistors, we will be able to calculate various parameters of the transistors. For example, we can calculate what is the resistance R0, what is the resistance Re, small re, which is the emitter resistance of any transistor. So these are the parameters which we will take for NPN and PNP transistor. So this is the scale current Is and this is the beta, which is having value of 200 for NPN transistor. VA, the early voltage for NPN transistor, is taken as 125 volt, while for PNP transistor scale current is same as for NPN transistor, but beta value is 50 and early voltage is equal to 50 volt. Here we have double collector transistor Q13. So for this double collector transistor, scale current of collector terminal A, this is 0.25 of normal scale current, we can see, while for collector B it is 0.75 of normal scale current. So this correlation we have to see. Now for DC analysis, we will replace all the external signals by their equivalent. So we will remove the input voltage. Input voltage applied at the base of transistor Q1 and Q2. So these terminal will be grounded. So voltage source is replaced by ground. So if we have not applied any DC input, any signal, so ideally we should get zero output because of high gain of op-amp. But we will get some output which will be close to the supply voltage, either plus VCC or minus VEE. Ideally, practically we will get voltage slightly less than VCC and VEE. So that is called plus VSAT or minus VSAT. So plus VSAT and minus VSAT is approximately 1 to 1.5 lower than VCC and VEE. So we will get some saturation voltage at the output. So overcome this problem, we have assumed that this op-amp will be operated in finite gain mode by using negative feedback. So because of application of negative feedback, output will be 0 as we have applied no input, no signal. So now coming to the reference current, which is generated by transistor pair Q11 and Q12. So here if we see, this reference current is generated by transistor pair 11 and 12 using resistor R5. So here we have plus VCC, this is minus VEE. So we will say the reference current will be nothing but the drop across resistance R5 divided by the resistance value. So we will say this is VCC minus this voltage, which is emitter base voltage of transistor Q12 minus base emitter voltage of transistor Q11, and then minus of minus VEE, and divided by resistance of value 39K. So this will come as IREF is equal to approximately 0.73 milliamperes. So we have taken these parameters. VCC and VEE are taken as 15 volt. Base emitter voltage of this and this transistor is taken as 0.7 volts. Now coming to the input stage. So if we see, the input stage consists of a Whittler current source, transistor Q11 and Q10, and because of this resistance R4, this is forming a Whittler current source. So now here this reference current is flowing. So if we are assuming high beta case, so we will say this will create some drop across base emitter of transistor Q11, and this drop will be divided in two parts, one in base emitter voltage of transistor Q10 and between this across this resistor R4. So now we can write what is the drop across this resistor. So we will say base emitter voltage of transistor Q11 minus base emitter voltage of transistor Q10 is nothing but the drop across resistance R4. So here we have written VBE11 minus VB10 is equal to IC10 dot R4. Here we have assumed high beta. So whatever current will flow in the collector of output transistor Q10, the same current will flow in the emitter of this transistor. So now we know the relation IC is equal to IS, the scale current, multiplied by exponential VB by VT. So by using this equation, we can write VBE and VB10 in this format, and this is equal to drop across the resistance R4. So solving this equation, we will get collector current of transistor 10 as 19 microampere. Obviously, because of presence of this resistor R4, IC10 will be less than the I reference. If this resistance would not have been present, then in that case Q10, if Q10 and Q11 both are matched, then we will get same current, means IC10 will be equal to IREF provided transistors have high beta. So we have calculated IC10. Now coming to the input stage. So here firstly we have assumed that total current in this branch is 2I. So now if we see this circuit, transistor Q1, Q3, Q2, Q4 both are NPN, this is PNP transistors. So because of symmetry of these two transistors, we will say the current 2I will be equally divided in both the branches. So this is current I for transistor Q1 and current I for transistor Q2. So both the transistor, input transistor Q1 and Q2 will have equal collector currents. Assuming high beta, there will be no current. There will be no current in the bases of transistor Q1 and Q2. So the same current will be available at these points, means the emitter of transistor Q1 and Q2. And same current is supplied to the emitter terminal of transistor Q3 and Q4. So we can get the idea of base current of transistor Q3 and Q4. So we know IE is equal to 1 plus beta times IB. So using this, we have assumed beta is much higher than unity. So we will say the base current of transistor Q3 and Q4 will be I upon beta P. Beta P, reason this is PNP transistor. Transistor Q3 and Q4 are PNP transistors. Now coming to this current. Let's say this is IC8 current, collector current of transistor 8. So this current, again this is transistor Q9 and Q8. So collector current is IC8. So this base current of transistor Q8 will be IC8 by beta P. So this current is flowing in this direction and this current is flowing in this direction. So we will say the current 2I is nothing but the sum of collector current of transistor Q8 plus twice of IC8 by beta P. So this current is this much. So now with the help of this we can calculate IC8 current. And because of current mirror action, the same current IC8 will be replicated in the output transistor of this mirror, that is IC9. So IC8 and IC9 both will be equal, and this is equal to the 2I upon 1 plus 2 by beta P. So if we will assume high beta, so here you can see if we are assuming high beta, so both the currents IC8 and IC9, both the currents will be equal to 2I. So let us calculate IC10, which is nothing but the output current of Whittler current source. So IC10 is nothing but this current, means the collector current of transistor 9 plus base current. So we can see these two base currents are additive. So this current in this branch is 2 times I upon beta P. So summing these two current, we can find IC10 is equal to IC9 plus 2I upon this much. So again assuming large beta, this is equal to 2I. So we can calculate IC8 and IC9, the collector currents of transistor 9 and 8. We know IC10 is equal to 19 microampere and this is equal to 2I. So I value will be 19 divided by 2. So this is coming as 9.5 microampere. So this way we will come to know that what is the collector current of transistor 1, 2, 3, 4. So all the 4 currents are equal in this pair. So this is the collector current of transistor 1, 2, 3, 4. So this is our target. And in same way we have calculated what is the collector current of transistor 9 and 8. Now another important point, at the same time we will see the negative feedback action performed by this loop. So let us see. Suppose because of any reason this current 2I increases. If this current increases, then in that case this current, which is equally divided between the collectors of input transistor Q1 and Q2, this will also increase. So current at this point will also increase. So we will say if 2I current is increasing, so obviously collector current of this transistor will also increase. So collector current of this transistor Q8 is increasing, so output current of transistor Q9 will increase. So if we see the current IC10, which is sum of collector current of this transistor and the base current, combined base current of these two transistors, since this is constant, so we will say if this current is increasing, in that case this combined base current will decrease. So if base current will decrease, so these currents will decrease. So this is, and again the collector current will also decrease. So here if we see, the increase in current 2I is compensated by this constant collector current of transistor Q10. So because of the decrease of base current, the increment of collector current is counterbalanced. So this is the negative feedback action performed by this loop. Now coming to the load side of input stage. So load side of input stage consists of transistor Q5, Q6 and Q7. So here this is current I which is coming out of transistor Q3, and this current is current I of transistor Q4, this branch. Again, assuming high beta for transistor Q7, there will be no base current in this branch. So we will say the complete current I will be available at this point. And again, assuming high beta for transistor Q16, which is the part of gain stage, so same current I will be available as the collector current of transistor Q6. Now, if this current is I and this current is I, both current are equal. So if we see the symmetry, so assuming both transistor Q5 and Q6 matched, and this is the common resistor shared by both the transistors, and resistance R1 and R2 both are equal in values. So here this is the perfect matching, because of which there is no change in the collector current of transistor Q5 and Q6. Now base current, since this is current I, this is current I, so base current is I by beta n, this is NPN transistor, and again this current is same. So we will say we have calculated up to this point. Now only term which is not calculated, that is the collector current of transistor Q7. So if we see what is the collector current of transistor Q7, so assuming high beta, the same current will be available in the emitter of transistor Q7, and this emitter current will be because of this current component, base current component, and the current flowing in resistor R3. So simply we have to find what is the current across resistance R3. So here net base current will be twice of I upon beta n, this term, and the drop across resistance R3 is given by base emitter voltage of transistor Q6 and the drop across this resistance, that is R2. So we will say VBE6 plus I dot R2 divided by R3 is the current flowing in this R3 resistor. Since we have idea of the collector current of transistor Q6, so by using formula IC is equal to IS exponential VB by VT, we can calculate base emitter voltage of transistor Q6. So if we are calculating base emitter voltage of transistor Q6, so this is coming as 517 millivolts. So putting this value of 517 millivolt, we can calculate what is the collector current of transistor Q7. So this will come as 10.5 microampere. Now coming to few definitions: input bias current and offset current. So here we have assumed high beta case, so there is no base current for input transistor Q1 and Q2. But in practical cases, even in case of high beta, there will be some base current. So if both the transistors Q1 and Q2 will be matched, their base currents will be equal, and this will be I upon beta n, NPN transistor. So I upon beta n. So we will say the bias current is average of these two base currents. So this is IB is equal to I by beta n. So this is bias current of one transistor. So average of this will be I upon beta n. So this is the input bias current. So what is the offset current? If both input transistors Q1 and Q2 are not perfectly matched, there is some beta mismatch in that particular case, means beta of transistor Q1 and Q2 are different, then in that case we will have different bias current. So this offset current is defined as the difference of two bias currents. Now coming to another very popular term which is known as offset voltage. So here if we see in the input transistor Q5, Q6, resistance R1 and R2 both are same. So if there is some mismatch between transistor Q1, Q2, Q3, Q4, Q5 and Q6 which are assumed to be matched, then in that case we will have some unwanted output voltage. So this unwanted output voltage is called output offset voltage. And input offset voltage is defined as a voltage which will be applied between the input terminals of transistor Q1 and Q2, that is bases, between the bases to nullify the output offset voltage. So if we have idea of output offset voltage V0. So input offset voltage will be nothing but the V0 divided by the differential gain of op-amp, and this will be the magnitude of input voltage which we will have to apply to nullify the output offset voltage. And obviously if this is plus, then we will have to apply negative of this much to nullify the output offset voltage. Now coming to the second stage. So in second stage, again assuming high beta. So here terminal B of transistor Q13, this is biasing the gain stage transistor Q16 and Q17. So assuming high beta, the collector current of this transistor will be same as collector current of transistor Q17, and also we note that scale current of transistor 13B is 0.75 times of conventional scale current. So we will say the collector current of this transistor is 0.75 multiplied by Iref, and this will come as 550 microampere. So this same current will be flowing in collector of transistor Q17. So once we have got the collector current, we can calculate the base emitter voltage of transistor Q17 by using same formula. So this will come as 618 millivolt. Now we have to calculate the collector current of transistor Q16. So here assuming high beta, this current will be equal to the emitter current of transistor Q16, and this emitter current is sum of current flowing in resistance R9 and base current of transistor Q17. So base current of transistor Q17 can be easily calculated. This will be collector current divided by the beta of this transistor, and this current across the resistance R9 is nothing but the base emitter voltage plus drop across resistance R8 divided by resistance R9. So we will say drop across resistance R8 plus VB17, which we have already calculated, divided by R9. So collector current of Q16 will come as 16.2 microampere. Now coming to the output stage. So here it is biased by collector 13A. Again, assuming high beta, no current will flow in the bases of output transistor Q14 and Q20. And this IS13A is 0.25 times scale current of transistor Q12. So we will say IC13 is 0.25 times I ref. So this same current, if no current is entering in the bases of transistor Q14 and Q20, so same current will come out of this branch. So this complete current is divided in this network of transistor Q18 and Q19. So we will get this current. So now this current, we will say this current is nothing but the sum of emitter current of transistor Q18 and sum of this current which will flow through resistance R10. So assuming base emitter voltage of transistor Q18 as 0.6 volt, means 600 millivolts. In that case, the current across this resistance will be 0.6 divided by 40, and this will come as 15 microampere. So once we have got the idea of this current, the emitter current of this transistor will be total current minus this current flowing through the resistance. So this will come as total current. This is equal to 180 micro, and IR10 is coming as 15. So this will come as 165 microampere. Now we can, since emitter current we have calculated, so we will say the same current will be available in collector of transistor Q18, assuming high beta case. Now we have to calculate the collector current of transistor Q19. So here collector current of transistor Q19, so we will apply the same formula. VBE19 is equal to VT natural log IC19 by IS. So by this way we will get this current as 530 millivolts. One more thing, initially we have assumed 0.6 voltage of base emitter voltage, and then we have calculated the collector current of this transistor. So this current is coming as 165 microampere. If we will calculate base emitter voltage of this transistor by taking this collector current, so this is coming as 580 millivolt, which is close to the our assumption of 0.6 volts. So now what is net base to base voltage? As we have already seen, the role of this network is to create twice of BBE drop between the bases of these two transistors. So we will say the total base to base voltage of this transistor is 530 millivolt plus 588 millivolts. So total base to base voltage is 1.18 volts. And note that this base voltage is also equal to base emitter voltage of transistor Q14 and emitter base voltage of transistor Q20. So we will say this value is also equal to this. So again, using the formula, we can write VBB is equal to this much, and here the collector current of this transistor is same as collector current of transistor Q20. So we will say IC14 and IC20 both are equal. And then putting these values, scale current of transistor 14 and 20, we can calculate the collector current of these two transistors. So in next class, this is complete DC analysis of 741 IC. In next class, we will see the small signal analysis of 741. Okay, thank you.